For the function y equals x squared minus 5x, estimate the tangent slope at the point p, 2, and negative 6 using technology. Include a sketch of the general secant line and the tangent line. So we already have a sketch here. This is our quadratic function y equals x squared minus 5x. This is our tangent line. It goes through this point here with the x coordinate of 2 and y coordinate of negative 6. So this is the slope we're trying to find, all this purple line here. This line in black, that's our secant. Now, the secant will originate at this point where the tangent is touching the parabola. And in this particular case, my secant here is ending at x equals 5 and y equals 0, but that doesn't have to be the case. They're asking for a general secant line. It simply means that we're starting over here at this point, and then we go out in some direction until we intersect the parabola. Okay, so it doesn't necessarily have to be these coordinates here, right? Now, the way we're going to approach this to find the slope of this tangent line is to use this secant to help us find that slope. And what we're going to do is, I'm going to move over to Desmos here so I can actually show you. Like that. So we are now in Desmos. We have exactly the same image here. And what I'm going to do is I have a slider over here. And right now it's set so that this endpoint of the secant line is at x equals 0 and x equals 5 and y equals 0. What I'm going to do here is, so clearly the slope of the secant line is different. It's almost perpendicular to tangent line. However, if I grab the endpoint, this endpoint right here, I can move it along the parabola like this. And as I'm moving it along the parabola, while I keep the left endpoint still stationary at that point where the tangent is touching the parabola, so as I'm moving that secant line and I'm moving this second point closer along the parabola, closer and closer to that point where the tangent line is touching the parabola, the slope of the secant will gradually become closer and closer to the slope of the tangent line. And you can sort of see now that as these points coincide, now they're very, very close to each other. You can see that. The slope of this secant line is now very similar to the slope of this tangent line. So what I just did here, as I moved from up here and I moved it down this way, I approached the point of tangency from the right. I started over here and I approached it from the right. We can approach it from the left too. So we can have a scenario where we have the secant going up like that. And now the slope of this secant line is different from the tangent line. But as I'm approaching the point of tangency from the left, the slope of that secant line will slowly, gradually become closer and closer to the slope of the tangent line. So this is the basic approach that we're going to be using here. So this was just to visualize that. So now we're going to go back to the problem here. So we're going to approach this point of tangency from the right, like that. This point up here is going to gradually move along the parabola closer and closer to this point. We're going to do it that's from the right. We're going to also do it from the left, so we can have a secant that looks something like that. And then we're going to move this point here along the parabola towards the point of tangency. This would be approaching the point of tangency from the left. And so using it, approaching the point of tangency from the left and from the right will allow us to determine the slope of the tangent line. Okay, so we are going to write an expression for the slope of the secant line. And we're going to be using the slope formula. So I'm going to name these points. This point down here, the point that has coordinate 2 and -6, I'm going to call that point P. And the other endpoint of the secant line, I'm going to refer to that as point Q. Now the coordinates of point Q, the x-coordinate is simply x. Okay, so this is what we're varying, as x is approaching the x-coordinate of the point of tangency, which is 2. So 2 is right here. This is the x-coordinate of this point right here. As x is approaching this, we're getting closer and closer to that point, and the slope of the secant becomes closer and closer to the slope of the tangent. So that's our x-coordinate. The y-coordinate of point Q is simply going to be x squared minus 5x, because we're following along on the parabola. So it's going to be x squared minus 5x. So we're using the slope formula. The slope of the secant line connecting points P and Q is going to be the y-coordinate of Q minus the y-coordinate of P over the x-coordinate of Q minus the x-coordinate of P. Now we plug in the expressions that we have. The y-coordinate of Q, so that was x squared minus 5x. The y-coordinate of P, so that's the y-coordinate of the point of tangency, it's -6. We have the x-coordinate of point Q, that was x, and the x-coordinate of point P, that was 2. We now drop the brackets in the numerator and simplify. And if we look at the numerator now, we have a trinomial that can be factored. It can be factored into x minus 2 and x minus 3. -2 times -3 is +6. -2 plus -3 is -5. Denominator is just x minus 2. We can now cancel the x minus 2 binomial, and we're now left with x minus 3. We will have some restrictions here. Specifically, x cannot equal to 2 because of this rational expression right here, the denominator right there. So this expression right here is a simplified expression for the slope of the secant, or specifically for the slope of the general secant. So this is a simplified simplified expression for the slope of the secant PQ. So now what we're going to do is we are going to do these two approaches we're talking about. We are going to be approaching the point of tangency from the right and from the left, and that way determine the slope. So we're going to approach from left. Approach x equals 2 from left, and from the right. Okay. So we're going to have our x coordinate here, and we're going to have our slope here. Our slope is defined as x minus 3. So when we're approaching from the left, we're going from over here somewhere and approaching this point here. We're not going to start this far away. We're going to start at perhaps 1.9 right below 2. X minus 1.9 is negative 1.1. Now we're going to go closer to 2. So we're going to put 1.99. X 1.99 minus 3 is negative 1.01. We're going to do one more, 1.999. 1.999 minus 3 is negative 1.001. And then if we go all the way down to 2, 2 minus 3 is negative 1. So as we're approaching that point of tangency from the left, the slope tends to negative 1. We're going to do the same thing, but now from the right. So we're going to start a little bit above x equals 2. We can start with 2.1. So it's going to be 2.1 minus 3 is negative 0.9. The next one, we're going to now go a little bit closer. So it's going to be 2.01. 2.01 minus 3 is negative 0.99. One more. 2.001, we're very close to 2 now, is going to give us a slope of negative 0.999. And again, if we go all the way down to 2, 2 minus 3 is negative 1. So what this means is that as x approaches 2, the slope m approaches negative 1. So our conclusion here is going to be that the slope of the tangent line equals to negative 1.